So they're saying, first of all, sine of 2x plus 1.
Yeah.
Let's integrate that. So we want the integral of what? Sine of the whole of 2x plus 1.
Yeah.
So if we were to differentiate whatever it is we're getting, we would get sine of 2x plus 1.
Yes.
Wondering what that is the derivative of, aren't we? Okay, what do you think we should write up here for the integral of sine of 2x plus 1?
Well, it will be a product.
Would it?
No, sorry, it would be a chain rule, because
That's right.
sine is an outer function, so you would get a chain rule of some sort.
Yeah.
One of them would have to be minus cos.
Good.
Because, yeah, well.
When you say one of them,
well, the outside function would have to be.
Good.
Yeah.
Well put. Yes. So we think it's minus cos of the inner function, which is 2x plus 1, yeah?
Yeah, and then that, whatever that is, multiplied by the integral of 2x plus 1, which would be...
yeah, I think you mean the derivative, but fine, yeah.
The derivative of... oh, yeah, no, sorry, I do, yeah. And then 2x plus 1, which goes to x squared plus 1x.
You're integrating the inner function, are you?
Oh, no, sorry, differentiate, so 2.
Okay. So what then? Are we done? Can we put plus c and move on?
I don't think so, because then would you? No, because it would go to 2x. You would have 2x. Sine 2x plus 1 times 2x for the
2x. Oh, do you want an x here?
Yes. Well, actually, no. Sorry, I don't. No.
No, that would be a 2, wouldn't it?
Yeah, actually, so it would be just plus c.
Well, then, is this equal sign holding?
Oh no. No, it's not.
So when you differentiate minus cos of 2x plus 1, we're not actually getting what we're meant to get as the derivative. I mean,
no, because oh no, because minus cos 2x plus 1, and then you have to. Oh.
I mean, here's what we're meant to get when we differentiate.
Yeah. No, I've just realised. Why is that?
So if this is what we're meant to get when we differentiate our integral, this here.
Yeah.
What's wrong with this?
It's missing. Well, it's 2 times the amount, but it's obviously
right.
It's got times 2, but obviously that
Well,
that can't, because it can't. Yeah.
Sorry.
No, nothing. It just means.
Well, that is precisely what's wrong with it. It's double. Yeah. So how can we restore it to being just sine of 2x plus 1?
Well, divide by 2, but I don't know why you would.
Sorry?
The only thing I can divide by 2, but I don't know why you would.
You don't know why? Sorry?
Why would you be dividing by 2?
So that the result is what we need it to be. But now we haven't quite got the derivative of exactly this up here, have we? What have we really got the derivative of down here now? Not exactly this anymore, now that we've put this half here. Before the times half there,
Yeah.
had exactly the derivative of that. The trouble was
Yes.
the derivative of that wasn't this. But if we make this what it was again, now we haven't quite got the derivative of that.
Yeah, no, I see that.
But what would this be the derivative of?
I'm trying to think. Minus a half. Cos.
Exactly.
Yeah.
Now it's okay, isn't it? Let's test by differentiating. Minus a half cos of something differentiates to
Half sine.
a half sine of the thing.
And then the rest works out.
And yeah.
So okay, yeah.
So we are done. So the integral of sine of 2x plus 1 with respect to x is that plus c. Always when you integrate, check straight away by differentiating.
Yeah.
And the point is, usually, you'll do that before you're finished, because checking by differentiating will be part of a process of trial and improvement.
Mm-hmm.
So
yeah.
you're kind of guessing, finding out what's wrong with it, making an adjustment, and then make a corresponding adjustment, and so on.
Yeah. Wait, is there a way of doing this where you get, because obviously that one, it is
Okay.
trial and improvement.
Yep.
Is there a way of integrating where you just get straight away to the, like, is there the equivalent of the chain rule, but for integrating?
Kind of, yeah.
Where you
It's
straight
overkill. But yes, you could say, okay, instead of thinking of it as blob here, you could call that u. You could say, okay, if 2x plus 1 equals u,
yeah,
then du dx equals what? 2. And then pretending this is a fraction, we could make dx the subject here. First of all, we could make du the subject, and that would be what?
du over 2 equals dx.
Yes. So then we could literally say, okay, we'll swap the dx for half du. Okay, so we literally swap 2x plus 1 for u, and we say we're doing the integral of sine u times a half du.
Yeah.
And then we've, in a way, we've prepared the ground there by putting the half down there already.
Yeah.
And we will get that.
Yeah.
We'll say, what's the integral of a half sine u with respect to u?
Minus cos u.
Minus a half cos u, yeah.
Minus a half cos. Oh, yes. Yeah, minus a half cos u.
Right. 3e to the 2x, integral of 3e to the 2x. So with respect to x, close the bracket. So how shall we pass?
Is that what the dx means? Does that mean with respect to x? When it says dx on the end, does that mean with respect to x? Just when
yes, unless you're doing this trick here, in which case you're hoping it means more than that. But yes, I prefer personally to think of it as the closing of this bracket.
Yeah.
Which is just saying the integral of with respect to x, yes.
Okay, yeah, no, that's fine. As long as that's, yeah. Right. 3e 2x, okay. What would differentiate to give that?
Yes. What's the inner function really?
E to the 2x.
I would say 2x itself is the inner function.
The 2x. Yeah.
So we expect that, you know, when we consider the basic
EX.
dealing with the outer function itself is E.
Oh, we'll go to 2e2x, wouldn't it?
On the way down, yes.
Yeah, on the way down, I mean. Oh, sorry, but you want to, oh, no, actually, so it'll be e to the 2x again. Would it? Oh, wait.
So the on the way down, we could think of this as du.
Yes.
I beg your pardon. We could think of that as dy du. And then you know that when you, with the chain rule says multiply by du dx. So du dx would be
e to the.
no du dx. The inner function with respect to x would be.
Oh, 2x.
Would it?
Oh, 2.
2. 2 is du dx.
Yes.
Okay, that's, you know, that formula for the chain rule, dy dx equals those things. That's the differentiating, isn't it?
Yeah, yeah. So
now we're working backwards through the chain rule. Can we make this equal sign hold again?
What do we? Oh no! So we need to half it.
Yeah.
Half times, and that means that you have to put a half. Does that mean you have to put a half on the e to to 2x again? Or...
Yeah, but I mean, we haven't really got any of that yet, have we?
No.
I mean, up here, if we've got e to the 2x, that'll differentiate to 2e to the 2x. So what will differentiate to 3e to the 2x is our problem.
What would differentiate to 3e to the 2x? Yeah, that. What am I missing?
So now we're in a position to say, let's make the equal sign proper again. What do we need to multiply by?
Oh, 3/2. Would it be 3/2 to?
Yeah, good.
Yeah. And that works.
Well, we'll check straight away. 3/2e to the 2x would different with respect to the whole of the inner function. It would be 3/2e to the 2x multiplied by the inner function. That cancels the 2, and you've got 3 as required. 3 of them. Okay. 4e to the x plus 5. Integral of 4e to the x plus 5 with respect to x.
Yeah. Okay, so the inner function is obviously x plus 5.
Yeah. Good. And the outer function?
The outer function is 4e.
Yeah. So with respect to the inner function, or u, with respect to u, we get
1. No, sorry. X squared plus 5x.
So what are you doing? Integrating the inner function?
Yeah. No. Yeah.
That's the wrong way around, isn't it? We integrate the outer function.
Oh, right. Okay, integrate the outer function, so you would get... oh, yeah, sorry. So, 4e to the u again.
Yeah.
4e to the x plus 5, and then
the inner function is going to spew out what in a derivative?
Times x squared plus 5x.
You're integrating again.
Oh no, sorry. X. No, 1.
1.
1.
So yes, we do apply the chain rule, but the inner derivative is only 1, so it really makes no difference. We still think of it as a chain rule differentiation and integration working backwards. But sometimes the inner derivative is 1, which is fine.
Yep.
Job done. D cos of 1 minus 2x.
Might as well do. Actually,
yeah,
do this one. Okay, yeah, do this one, and then.
Certainly, we could move on.
Maybe after this one, we could go to the next sort of couple or something. I don't know. We'll see. Anyway, okay.
Or we could do these orally, mentally.
No, I'm just okay. No, let's just do this one, and then.
Okay.
Right. The inner function is obviously 1 minus 2x.
So the
outer differentiate sine x goes to cos x. So yeah, you just have sine 1 minus 2x.
Yeah.
And 1 minus 2x differentiates to minus 2.
Okay.
Which, so you would have to do minus 2. Oh no, sorry, to balance it out, you would have to do, what have we got? Oh, times minus 2 again?
Like that?
Yeah. Does that? Because then you get minus 2 times something, and then. Oh no, so you divide by minus 2.
Yeah.
Why am I timesing by minus 2 to get rid of? Yeah. Times by divide by minus 2.
Yeah.
Or times by a half. Minus a half, yeah. And then okay, so and then we just have to put minus a half cos minus a half sine on the top, yeah.
Plus C. Pretend you're differentiating it and make sure it works. So that would be minus a half cos of whatever multiplied by minus 2, which is going to cancel the minus a half.
Okay.
It's going to be what we needed.
I'm starting to get the idea now. It's just at the beginning I was trying to do the inner function first.
Yeah.
Which doesn't obviously work.
Okay,
right.
Thank you now.
Would you say that H, I, J on question 1 are any more difficult?
Yeah, probably. They'll probably be well worth doing.
Okay, do those then.
So, I mean, do you happen to know what sec squared is the derivative of, though?
I have forgotten. It's not cot squared, is it? That might be by memory just completely.
No, but it's tan.
Oh, it's tan.
Which is an interesting, yeah, the derivative of tan is sec squared. It's always worth differentiating tan to find out why that is, by doing it as sine over cos.
Mm-hmm.
And using the quotient rule or product rule, you'll get, in the end, sec squared. So the inner function here, well, interestingly, there's 2 inner functions. Or is there? No, not if we think of sec squared as the derivative of tan. I take that back. Yeah, that would have been a bit of a headache. So bearing in mind the outer function is just sec squared, which is the derivative of tan, we can just go as we did before, really. So that is no harder. The answer is?
Tan, yeah, tan, and then 2 minus x, and then that 2 minus x goes to -1.
Yeah.
Times by -1, you multiply. No, so do you divide by -1?
Which is like? Timesing by -1.
Timesing by -1, yeah. And then that means you just have to put minus tan 2 minus x.
Yeah. Plus c. What else we got? Cosec 2x, cot 2x. Whoa. Yeah. I don't know yet.
What was it? And then cosec.
I don't know. Before doing some algebra with it, I'm not seeing it. Cot 2x. So.
Cosec 2x, cot 2x.
Or maybe we're going to have.
Oh, this is no. So I'm pretty sure this is one of the rules actually that I'm just supposed to know.
Yeah, you're right.
I really do think
Sec
it
x,
is.
tan x, cosec x, cot x. Yeah, of course. Yes, you're quite right. So it's.
That's just a case of me learning a rule, but I can't.
Well, yes, this is a rule. I mean, it's a shame to do it like that in a way, but it's fine. Yeah. Well, what it is let's just check why that is. That cosec, or 1 over sine, which is sine of anything to the power of -1, would differentiate to the same. Anything to the power of -1 differentiates to what?
Sorry, sine. What different? I didn't hear till I something.
Sorry, anything to the power of -1 differentiates to, with respect to the thing, it differentiates to what?
-2.
Pardon?
Is it to the -2 or am I being?
To the -2, yeah?
Yeah.
And it would be negative as well, wouldn't it?
Yes.
And also, what do we get? On account of the chain rule. If we're differentiating. Cosec. Sorry, yes, I didn't make this clear. What I'm differentiating is cosec of an angle.
Okay. Oh, sorry. Now it makes sense. Okay.
Yeah. No, I completely left that unexplained. Sorry.
And then it will be times 1 because theta. Would theta just go to 1?
But the inner function is sine theta.
Oh, the inner function is sine theta, so that goes cos theta.
So, and that equals minus cos over sine squared, doesn't it?
That was, yes.
And that equals, another way of saying that is cos over sine times 1 over sine.
Times 1 over sine theta, so tan.
And another way of saying that is
minus tan.
Cot, though.
Minus.
Cos over sine, it's.
Oh, it's not tan.
Rather than tan. So it's minus cot theta.
Minus cot theta.
Cosec theta.
Cosec theta.
So we've just proved that minus cot theta cosec theta is the derivative of cosec theta. So if we put a plus there and there.
Yeah.
And there and there, we need to put a minus here. All right. So what are we getting here? It's a fact that tan differentiates to sec squared, and it's a similar fact, which you can verify like that, that minus cot differentiates to cosec cot.
Yeah, so minus cot 2x. Would you?
Yeah, but then just a bit of a chain rule there because there's a bit of an inner function.
Oh, right. 2x goes to what does 2x go to? Differentiate to 2. So
right.
Then you'd have to divide by 2, so you'd get minus a half cot 2x.
Yeah. And then check straight away by differentiating. Well, we've just discovered that cot differentiates to minus all of that. So minus cot differentiates to all of that. 2 spewed out from the chain rule, cancels that half, back to where we were meant to be.
Yep. Okay.
All right, moving on, perhaps.
Yeah. I'm just trying. Oh, okay. I've just remembered where we got up to. So, of questions 2 and 3, what difference do you see? Are they much harder, or are they just the same thing but like 2 of them?
Yeah, good point. That is a good point. Where you can, just do one integral plus another integral, and you can do them one by one if they're being added or subtracting. Yes, added or subtracted. Yes. I don't know about C. What's happening there?
For example, for 2D, it would be quite difficult. Or would it be quite difficult to work out what what it's the derivative of?
Yeah. What do you reckon? 3. Oh dear. I don't know. Because oh, sorry. By the way, error. Oh gosh. I just what we proved here was that this was the derivative of the cosec. And I went and wrote that, didn't I, as cot? Sorry. I remember writing that as cot.
Oh.
My brain didn't complain.
Oh.
But it should have. Sorry, that's a cosec there, not cot. Just a typo for that. All of this was good, but it was showing that what we were starting with here was the derivative of cosec. I just did a typo there, sorry. Not cot.
Okay.
Sorry, anyway. I just suddenly realised that.
Yeah,
and why did I realise that? Because I'm looking at this one here. Where was it?
Yeah, because I'm trying to think, because all of them are integrate the following, and they're all like 3 over 4x minus 1 and stuff like that. And I'm thinking, what would you?
Yeah, because this you're going to cut into 2 probably. Let's have a look at that D. I think it needs cutting into 2 fractions, splitting into 2. So
Does that? Which one? Sorry, do you mean 2D?
2 different types, which is interesting. So, sorry, this D one you were talking about?
I was thinking about 2D, but I honestly don't know.
Yeah, it's worth doing.
Are they all quite similar in question 2? Are they?
They're all different enough for where we are at the moment. They're not a waste of time. On the other hand, I do, you know, this is the trouble. That's why I'd rather do an exam paper where you're, you know, if you're in a textbook, it's always complacent, really, not to do every single one.
Yeah, I mean, the only reason I am going through the textbook like this is because it corresponds more with what we do in lessons. Yeah. So I can see where we are, and I can easily, because I don't know the maths, I can tell you this is what I want to do. Whereas I can't completely tell you if it's just an exam question, because I can't go through the exam question in my head before I know how to do the topic. So I don't know if it is that topic. So yeah, that's
this one. 2 cos half x all over sine was squared, was it? Sine squared of a half x. So it is working backwards through the chain rule, in which case what do we suspect is the inner function? Oh gosh, hang on now. Yeah. Well, we suspect the inner function is, bearing in mind we could split this into 1 over sine squared, we could write as cosec squared, and that might remind us, and this is what reminded me that that's what I was confusing with this one here. You see, I was just looking at this and thinking, oh, well, we've got cosec squared down here, and we know that cosec squared is the derivative of what? And do you know? You know that sec squared is the derivative of tan. And sec is 1 over cos. Cosec is 1 over sine, so it kind of makes sense that cosec squared is the derivative of cot. Or is it minus cot? Let's find out. By differentiating cot.
I don't know. Okay, differentiating cot.
Which is cos over sine.
Cos over sine.
You could use the quotient rule. Personally, I would do this.
Oh.
No, I wouldn't. Oh, hang on. Yeah, I would. And do the differentiate with the product rule. What shall we have here?
Differentiate with the product rule. So we would get.
Oh, by the way, are you clear what I've done up here?
Why is cot theta cos theta over sine theta?
That's just the definition of cot. It's 1 over tan, and the reciprocal 1 over means reciprocal, and tan is sine over cos. Therefore, cot is cos over sine.
Oh, yeah. Okay, yeah, no, that makes sense. Okay, so right, so we're now doing the D. differentiating cot theta.
Yeah.
So equals cos theta. Cos theta would go to minus sine theta.
Good.
And then the sine theta would go to cos theta.
Right, but don't forget the product rule. You can't, if you're differentiating a product, you can't just say it's the product of two derivatives. So
yeah,
you differentiate that one and leave this one alone.
Yeah, so my sine theta minus 1 to the minus 1.
Differentiates to what?
That differentiates to cos theta. Is it minus cos theta to the minus 2?
No, you've got to bear in mind you've got a compound, a composite, so it's the chain rule. So what does blob to the power of minus 1 differentiate to with respect to blob? Or u? What does u to the power of minus 1 differentiate to with respect to u?
Minus u to the power of minus 2.
Yeah. So you've got to the power of minus 2. But we've got to multiply by the derivative of the inner function, really, haven't we, as well? Because that was that was a chain rule differentiation.
Yep. So then we would get cos theta. Cos theta on the end as well.
And what should we have here and here?
The undifferentiated things.
Yeah.
So
that'll be cos.
Yeah, and the other one will be sine theta to the minus 1.
Or we're going to need a common denominator now, so we could put that in right away. We could say instead of just having 1 over sine, we could have sine over
cosec,
sine squared.
Sine over sine squared, that also works.
Because this is over sine squared, really, isn't it? Power minus 2 here means over sine squared.
Yes, yeah.
So, what's this fraction?
That is minus sine squared theta.
Yeah.
Over sine squared theta.
Over sine squared theta. And then what have we got here over sine squared theta?
1. Minus 1. Oh my.
But the whole thing?
Oh, the whole thing. Cos squared theta.
Yeah.
No, yeah, cos squared theta.
So, and it's a minus, isn't it? Minus cos squared theta.
Minus cos squared theta.
Over sine squared theta. Which is why we now see that cot differentiates to, in the end, we were differentiating cot, weren't we? Started up here. Down there. Now, bearing in mind that that's minus both of them, so we could put it like that.
Oh, one of them goes to 1. And is it minus cos squared theta? Oh, minus cos squared theta over sine squared theta. Oh, no. Wait.
Yeah, but sine squared plus cos squared equals?
1.
Yes. So in fact, we just got 1 on top. So it's 1 minus 1 over sine squared.
Sine squared theta, which would make it minus cosec.
Yes, good. Which is what we want to use. We're saying, what is a cosec squared? What is cosec squared the derivative of?
Oh, yeah.
Minus cosec squared is the derivative of cot. So we've now clarified that what is plus cosec squared the derivative of?
Cosec squared is derivative of minus cot.
Yes, good. So we've got minus cot of whatever is inside, which happens to be half x, yeah?
Is that just what's inside? Is that? Yeah, it is, isn't it? Okay. So Then what have we got? Have we got is the bit that we've got? Is the bit that we haven't done yet? 3 minus 2 cos.
Yeah, it doesn't take care of all of it, does it? When I put this down, they did say we were going to split it into 2 fractions, but I seem to have forgotten to do that. I've forgotten that we were going to have to. I now see that we're going to have to, but that's fine. What we'll do is, yes, it is fine. So we can say what we'll deal with first is this half of it. You see what I mean? That's 3 cosec squared, isn't it?
Yes.
All right, so let's just forget about that awkward customer there, which is going to get done differently and separately. But we can just finish off this one. As far as this part of it goes, we know that cosec squared integrates to cot minus cot. So should we just finish this off? Is this working yet? I'll just put a 3 up here or what? Minus 3 cot? How many cot up here?
Minus 3. Yeah, no, it is. Actually, wait. How many cot?
The only thing is we've got to take care of the du dx.
Yes.
The inner function derivative.
Oh, yes. Okay, so that goes to a half. So we have to times by 2. So we get 6 minus 6 cot.
Exactly. Well done.
Yeah.
Minus 6 cot up there, right? Okay, and then the other stuff that we were ignoring. I'll just get rid of this. Hang on. Don't need that, do we? Right. So what are we left with? We've got 3 over sine squared half x minus the rest of it, which we shall pass rather differently. Okay, this is clever, what they're making us notice here.
Yeah.
So we've done that by doing the integral of cosec squared and knowing that already.
Yes.
But we're going to pass this one a bit differently and call it 2 of or rather, I'm not sure about what to say about the outer function yet, but I do know that the inner function, we're going to be subtracting something where the inner function is, I'm going to think of it as sine x. Yeah.
Sine x.
Whereas here, I just called it 1 over sine squared x, cosec squared x already. But if the inner function here is basically sine, what's the outer function?
For 2 cos.
No, I'm going to ignore that for now. I'm going to hope.
Oh, you're looking at the.
But if sine squared is on the bottom,
yeah,
that's like saying that we've got sine x subjected to what outer function?
Oh, to the minus.
Yes.
2.
To the power of minus 2. Well done. Fine.
So the minus 2. Yeah.
Right. In which case, if what we're integrating is something to the power of minus 2, what'll it go up to?
Minus to the power of minus 3.
Sorry. You make sure the power goes up, not down.
Oh. Yeah, minus 1. Sorry.
Yeah, it's tricky that one.
I'm thinking 3 is bigger than 2, but then obviously.
No, that's right. That's what happens. But you'll learn to.
Yeah, I won't be the first one to have made that mistake. Right, and then.
Oh, and this was a half x, by the way, wasn't it? Ooh.
Yes, it was a half x. Yeah.
We've got another little further inner function.
The half x. Oh, okay, and then the inner function of that is a minus sign. You get minus cos.
Well, the inner function is just sine, not minus sine.
Oh, yeah.
This is outside there, isn't it?
Right. So you get cos.
So we'd get cos, but then we'd apply the chain rule again inside, wouldn't we?
Yeah.
So it'd be cos of a half x times.
Half.
Times a half. Good.
And then you'd get, yeah.
And then how does that compare with what we needed, which was 2?
2.
But then that's nearly fine, because what we had was minus 2 cos of a half x. But instead of writing 2, we should probably write, because of this half now, here.
Oh, times by. No, wait, instead of writing 2, we should probably write.
Let's say we had this 2 here.
Yeah.
This was what we wanted to integrate. And we're fine with this. We like this. Oh, and it'll be 2 of them as well, won't it? I suppose that minus. Oh, yeah, that's a point. We're minusing all of that, aren't we?
Yeah.
But we did have a minus here. And if we had the 2 in there as well, it would be minus 2.
Yeah.
But now that we've got this half here, we need to cancel that by doing what?
Dividing by a half.
In other words?
Times it by 2.
Yes. So in other words, we want
4.
A 4 here and here as well.
Mm-hmm.
So that would be minus 4, because we said we'd had a minus for the sign.
Yep.
For that business there, and we're taking the whole lot, but that's what we've got. It'll simplify a little bit, won't it? It'll be minus 6 cot of a half x plus 4 over, or either 4 over sine of half x or 4 cosec half x.
Yeah, either way is the same thing, right?
Yes.
So that was, you know, as I say, once you start working properly through a book, well, if you're going to do them all, yeah, do them all. But if you're not, and I wouldn't, I would do an exam paper and just keep getting a lot of variety. But then there's no way you're justified in skipping anything in one of these banks. So they're all different.
Yeah, I mean,
so this, you know, you can't win really. But anyway, that's good. That's another good example.
yes.
And where should we go next?
What exercise 11B, and then what's the next page?
Yes.
Oh, okay. Exercise. Oh no. Yeah. Okay.
Yeah, more of the same. Should we do these?
There will be exam questions, and should we do one of the exam questions?
Sure. So number 6, given that the integral from 3 to b is what it is, etc. Find the value of b.
Yep.
Okay. So how would you do the integral from 3 to b? That stuff all squared.
2x minus 6.
Now you could do it the boring way. What would be the boring way?
What would be the boring way?
Yeah.
It would be chain rule.
No, no, that's fun. The chain rule is fun. Boring would be to expand it and do it as a polynomial.
Oh, hey. Yeah.
So let's use the chain rule. Sorry, and again, so the function up here is?
The function up there is if it's the 2x to the 2x minus 6, it's just 2x minus 6 is
Careful.
Or 2x squared minus 6.
What happens to the power on the way up?
It increases, so
yes.
2x minus 6 to the cubed.
Yes.
To the power 3, yeah.
What, like that?
No, because there's times 2 on the bottom, like on the.
Yeah, but also if you were differentiating, that's true. You do want to take account of the times 2 here. But
yeah.
Also, when you differentiate, what are you going to get? How many of the square?
How many? What do you mean by how many of the square?
Well, for example, what's the derivative of x cubed?
The derivative of x cubed.
Not x squared, is it?
3x squared. So it'll be so you'd get 2. The derivative of 3x squared.
I mean, as things stand, it's going to differentiate to give you 6 of this square here.
So I feel like I'm missing something really obvious.
Well, I mean, it's a process of trial and improvement, isn't it?
Yeah.
Our best guess so far is that we've got blob cubed.
Yep, and then
The integral of that stuff.
Yeah.
But when we check by differentiating,
yeah,
which it's never too soon to check.
2x squared.
Yeah, we get 3 blob squared times 2.
Yes.
Which is precisely 6 times as much as we want.
Oh, right, so we need to divide by 6.
Yeah, then we check that, what we'll get is a 6th of all that.
Yeah.
Now, if we evaluate that between 3 and b, it should be better.
Yeah. And then, okay, right, so equals yeah, 6 2b.
And then we're told that that equals 36.
Why 0? Actually, no, you've got to. 1 second.
Yeah, the 0 was from subtracting the 3 version. The expression.
Oh, yeah, okay. And is that what it came out as? I haven't done it yet, but it's okay. Yeah, no, that's fine. So equals 36, and then it's just a matter of solving an equation, isn't it?
Yeah.
Right, so 6 times 36, so essentially 6 cubed.
Yeah, indeed, yes.
6 times 36, 206. That's my maths one.
216, but
oh wait, no. Okay,
you're going to cube it in a second anyway, so cube root it, so there's no need to do it. But
oh right, 6 cubed and then 2b 6 plus 6. Yeah, and then b equals 6. Okay, yeah, b equals 6. Right. I have a feeling we're going to be doing a little bit more of this next week, just because. What date is next week? Wednesday and Thursday.
Yeah. I think the 6th and 7th.
For 6th and 7th, that doesn't ring a bell for any reason. I'll tell you, obviously, if something happens that means I can't do the lesson, but nothing. Yeah, it doesn't ring a bell. So, yeah, I think it might. We'll probably, because I think there's one more type of. The next exercise, so we were just doing 11B, I think. I think what we'd actually got up to in class was 11C. So I think that what's 11? 11.3, using trigonometric identities. Does that?
For integration.
Yeah.
Yeah, I mean, it's just.
Is it just the same thing, but some of them are rules?
Yeah, it's just saying here's some more where you'll find that you have to use some of those trig identities that you already know from other contexts. It's just mixing with the other stuff as well.
I mean, yeah, I mean, it's probably worth doing next week for an hour, and then we'll see after that hour. So anyway, yeah.
Yeah.
See you then.
Okay, great.
All right. Yep.
All right, have a good week. Happy New Year, indeed.
Yeah, see you in the new year.
Yeah, cheers, Alex.
All right, bye.
Bye.